Well, I think we are already here. Thank you very much for coming for this new date of the colloquia seminars of the ICMM. First of all, I will only to recall one thing, is that all the students who want to have a certificate of attendance, please look at the QR in the telephone, and then you have to sign these forms after the seminar, okay? They are. So we have two speakers today, and we will allow only questions after the two talks, okay? You have to wait till the end to ask your questions, okay? And now for the introducing our speakers, I will let Sarah to make the presentation. Thank you.
Thank you, Rafa. Then thank you everybody to coming today to the first colloquia of this year that we delayed due to the construction works. But in reality, everything is working so well, then probably we could have this colloquia earlier. Today is dedicated to the Nobel Prize of 2025. We are in January of 2026, but I think that everybody could enjoy about the fantastic science that have been awarded last year. Then the first speaker is Ramón Aguado. He's going to talk us about the Nobel Prize in Physics. Almost everybody knows him, but I'm going to do a brief introduction of him, just for the new ones, especially the PhD students. Then the research of Aguado is focused on hybrid quantum materials and their applications in quantum technologies, with particular emphasis in topological superconductivity and qubits based on Majorana and Andrew states. Over more than 2 decades, he has established himself as international recognized expert in theoretical condensed matter. I don't know if you know, but he is one of the top 1% most cited scientists in applied physics worldwide, and also top 2% most cited researchers across all disciplines in Spain. Before joining to the CSIC, he carried out postdoctoral research in Rutgers University in the United States and Delft University in the Netherlands. In addition to his research activities, he has played an important role in scientific service and community leadership, and currently he serves as president of the Condensed Matter Physics Division of the Spanish Royal Society of Physics, as coordinator of the Quantum Physics and Matter program at the Agencia, and he also has been recognized as an outstanding referee by the American Physical Society. Then now we can enjoy about his talk about the Nobel Prize of Physics of the last year. Thank you, Ramón.
Okay, thank you very much for the invitation, Rafa and Sarah, and thanks, Sarah, for this nice introduction. All right, so yeah, today I will tell you a bit about the Nobel Prize in Physics 2025. This is about the early developments in superconducting circuits, and the title is Pendulums and Quantum X on a Chip. You will see why. All right, so this Nobel Prize in Physics in 2025 has been very timely, because in 2025 it was actually the year of quantum science and technology. So we celebrated 100 years of quantum mechanics because of Heisenberg, and some of you maybe recognize this face, this famous Heisenberg face. Of course, it's not the original Heisenberg, it was just a joke. So although quantum mechanics was developed early on, much before actually 1925, it is kind of established that the birth of quantum mechanics was originated by this groundbreaking paper by Werner Heisenberg on the quantum theoretical reinterpretation of kinematical and mechanical relationships. This is like the first formal step trying to develop a proper quantum mechanics. Together with papers with Born and Jordan, he developed all this matrix formulation that we know these days about quantum mechanics. And of course, in 1927, he developed the most important discovery by Heisenberg, which is the uncertainty principle, which I guess all of you know, or most of you know. And essentially, he received the Nobel Prize in 1932 for the creation of quantum mechanics, okay? And something actually very nice is that, you know, he developed the uncertainty principle. He published this in 1927, and just 1 year after that, in 1928, his first PhD student, Felix Bloch, defended his PhD thesis on the quantum theory of solids using waves to describe electrons in periodic lattices, what we know today as the Bloch theorem. So, you know, the applications of quantum theory were immediate, and actually in our field, in the field of materials, if we want, this was one of the first applications, actually. The first PhD student by Heisenberg was Felix Bloch, which is something remarkable, which probably some of you didn't know about. Anyway, this is the uncertainty principle. As I said, all of you know, or most of you know. This principle sets a limit on the precision that you can have to measure what we call these days as conjugate variables in quantum mechanics, like position and momentum. In quantum mechanics, you cannot have precise information about two of such conjugate variables. There is always an upper bound given by a constant of nature, what we call the Planck's constant. So the product of two variables like position and momentum should be always above this bound given by this constant, meaning that if I have very precise measurement on position, I have a strong indetermination on momentum, or the other way around. And there are other relationships for conjugate variables like energy and time and others that we will see along the talk. All right. So as I said, of course, Heisenberg was not the first who proposed these kind of weird ideas about quantum in kind of 100 years ago, more or less. The early ideas came actually by Planck. In the beginning of the last century, Planck explained the black body radiation, and this is when he actually introduced the concept of quanta, the concept that energy is not emitted continuously, but instead is emitted in the form of kind of packages, a form of quanta. This packets he called actually quanta. And actually, he was the first who made this relation between energy and frequency of the radiation, the frequency of the electromagnetic field emitted by black bodies with a given temperature, which back in the day was kind of an open question. And the constant relating frequency and energy was given precisely by this famous Planck's constant. Then it came the famous atomic model by Bohr, which we learn in high school. This idea that in atoms we have orbits around the nucleus of electrons, and this is the origin of the idea of atomic orbits and essentially all the ideas around the periodic table. Then 1921 we have the wave particle duality by Louis de Broglie, the idea that particles have always associated a wave in terms of a wavelength, which is the inverse of the momentum of such particle, again introducing the idea of waves. So all these ideas were around, but then in 1925 this is when Heisenberg kind of formalized everything in terms of this quantum mechanics. Then other important breakthroughs, of course, came with Schrödinger, with the famous wave equation of Schrödinger, and then also very important in 1928, this Paul Dirac, the Dirac's equation, which is also very relevant these days for us, like graphene, topological insulators, all these equations that we use in condensed matter, were developed in, of course, a completely different context in the equation by Dirac, where he was able to put together quantum mechanics and special relativity. So by putting together quantum mechanics and special relativity, you end up with the Dirac equation, by which you discover things like the spin, things like antimatter, the positron is the antiparticle of the electron, and these kind of things. All right. So quantum is everywhere. So, these days we talk a lot about quantum, like quantum is a new thing. No. Quantum is everywhere. We understand quantum very well. It's by far the most precise theory in nature that we have in physics. So we understand essentially all phenomena at different levels because of quantum mechanics, starting from, as I said, the periodic table, quantum chemistry, a lot of things we understand because of quantum mechanics. There is also the technology application of quantum mechanics, of course, starting from, transistors, lasers, you call it. I mean, there are many applications of quantum mechanics, of course, but these days we talk a lot about quantum in the sense of what some people call the second quantum revolution. So instead of using quantum to understand nature, to understand the microscopic behavior of nature at different levels, what these days we want is to use and to manipulate quantum properties, okay? To manipulate quantum coherence, to manipulate quantum entanglement, these kind of things. This is the idea behind this so-called second quantum revolution. And you all know about quantum computing, quantum communications, quantum cryptography, quantum sensing, all these ideas of actually being able to manipulate quantum at these levels. All right, and it's, these days it's everywhere in the news. There are many news every day at different levels, starting from science, basic science level, to technology. Even in economy, there are a lot of investors putting money in new companies. So for sure, there is a lot of noise around quantum. There is kind of some people think there is kind of a bubble. Some people think it's not. But anyway, it's becoming a huge thing, and many of us think that it may become a very relevant technology in the next few years. All right, so you have seen probably this kind of picture. This is this is actually from Google. This is a Google quantum lab, and essentially, these quantum computing labs, in particular in these kind of labs where they use chips or circuits, what you see typically is some dilution fridge full of cables, and somewhere here inside this fridge, this is without the cover, of course. The cover would be hiding everything, but without the cover you would see this kind of complicated system, and inside this kind of chip holder you would have something that we call a qubit, which is a quantum bit. This is a two-level system of different, there are many different implementations for such qubit, in such a way that when you take out signals out of this fridge, by very sophisticated electronics you can manipulate such qubit. For us, a qubit is just a two-level quantum system, and we talk about the Bloch sphere. The Bloch sphere is essentially a vector living in a surface of a sphere. So instead of having 1 and 0 of this standard digital electronics, this would be like the north pole of the sphere, and the south pole of the sphere would be the classical 1 and the classical 0 of binary electronics. We talk about the sphere, the Bloch sphere, which is essentially this complex vector living in the surface of the sphere. So you go from 2 points to a whole surface that you can cover with this complex vector, which is characterized by 2 amplitudes, the amplitude of being in 1, the amplitude of being in 0. So these are the two possibilities if you are classical, but in general you can be in any superposition between 0 and 1, and this is the idea of quantum computing. Using these strong superpositions, you can actually exploit this in quantum computing in a very powerful manner. All right. Today, as I said, there are many different implementations of qubits, of these qubits, quantum bits, many of them. But today I'm going to focus on circuits, on superconducting circuits based on superconducting materials, all right? essentially the working horse, the basic element of one of such superconducting circuits is a Josephson junction. And this Nobel Prize this year has been awarded by to the three awardees, as I will describe in a few minutes, for the early demonstrations of quantum behavior in such circuits. All right, so this is an image of a typical quantum computing lab. This time is the IBM quantum computer, very similar to the one they are already establishing in San Sebastián, in the Basque Country in Spain, one of these IBM quantum computers. Again, this is one of these dilution fridges. And if you look at this image, it's not that different from these very first images of the first experiments in Leiden at the beginning of the last century, 1908, where Heikki Kamerlingh-Onnes was able to liquefy helium. Right, the first experiments where helium was liquefied, and he was able to reach 4K, thereby opening the field of low temperature physics, of macroscopic quantum phenomena, if you wish, was originated in Leiden, which was known back in the day as the coldest place on Earth. So you see, if you Google it, you will see many pictures of very famous physicists always visiting Leiden, because back in these days, I mean, we are talking about 1908. This was an amazing discovery, an amazing technological progress back in these days. Very early on, since he discovered the ways of liquefying helium, they discovered this phenomenon of superconductivity. The idea that when you cool down a metal, a metal typically has some resistivity, but as a function of temperature, when you go down below typically the temperature of this helium, temperature 4 Kelvin, mercury, for instance, the resistivity suddenly drops and essentially goes to 0. So a metal below some given temperature, which we call critical temperature, becomes what Kamerlingh-Onnes already coined as a superconductor. It's a metal that can conduct electricity without any dissipation, without any resistivity. He actually got the Nobel Prize in 1913 for this discovery. This is the first important property of a superconductor: zero resistance state with finite temperature. So it's a non-dissipative, which is, if you think about it, it's a non-dissipative way of circulating currents in the metal. This is the first important property of superconductors. The second important property of superconductors is like they behave as perfect diamagnets. These supercurrents typically try to screen any magnetic field that you try to pull inside this superconducting metal. And you all have seen these very nice demonstrations that we do here. This is Maria Jose and Michel doing this famous levitating train from ICMM. This is a demonstration when you cool down a superconductor that this system behaves as a perfect diamagnet. So superconductors, non-dissipative current, and diamagnets. There is kind of a very sophisticated theory behind this explaining why metals can become superconductors, but the concept that we need today to understand what a superconductor is the idea that in a normal metal, you have electrons flowing through your material, but below this critical temperature, all the electrons, instead of repelling each other, they begin to get attracted in pairs, what we call these days Cooper pairs. So electrons attract to each other, two electrons with different spin will form one of such pairs. And at very low temperature, there is a macroscopic state with billions and billions of such Cooper pairs which form a unique wave function. So a unique wave function of billions of electrons which are forming such Cooper pairs. And this macroscopic, this emergent ground state at low temperatures is described by what we call the order parameter, of the BCS theory, BCS, Bardeen, Cooper, and Schrieffer, who are these three gentlemen who who developed the theory of superconductivity, you can understand pretty much everything in terms of what we call this order parameter, which is a complex quantity in terms of an amplitude and a phase. And this phase is going to be very important for this talk. So this huge macroscopic quantum wave function has a common phase. So all the electrons are paired together, they form Cooper pairs, and they have a huge coherent macroscopic quantum wave function that shares a same phase. All the states become a global common state with a given phase. So again, another Nobel Prize in physics. So this is the second Nobel Prize in physics because of superconductivity. In this case, for the Nobel Prize in 1972 for the BCS theory, Bardeen, Cooper, and Schrieffer got the Nobel Prize. And another interesting fact that maybe some of you don't know is that John Bardeen, this gentleman here, is the only person in history who has received received two Nobel Prizes in physics. The first one he got for the invention of the transistor effect in semiconductors, which is also a very relevant discovery for our world, right? I mean, we cannot understand our society without digital electronics, semiconductors, everything. So this was the first Nobel Prize in 1956 for the invention of the transistor, and then he got a second Nobel Prize for this theory of superconductivity. All right, so we have this macroscopic state, which all the electrons condense in Cooper pairs, and they are characterized by a global phase. This wave function is characterized by a global phase. Now, if we put two electrodes, two metallic electrodes that become superconductor at low temperatures, and we have a tunnel junction between two superconductors, this tunnel junction is essentially characterized by a superconductor with a given phase A, and another superconductor with another phase B, and the phase difference B minus A, as soon as I have a phase drop in the junction, a phase difference in the junction, I develop this supercurrent. So these superconducting currents, these currents without dissipation in superconductors, can be understood as changes in the phase of the condensate. So anytime you have a change in this phase, like for instance in this junction, you immediately have this superconducting flow without any dissipation, and I insist many times, without any dissipation, you have superconducting flow, which goes as the sign of the phase difference. So we have Ohm's law, we all know from high school, Ohm's law, the current is proportional to the voltage, and the inverse is the resistance. When you lower the temperature, your IV characteristics becomes very different. At zero voltage, you have a finite current, which is this supercurrent I've been discussing, what we call the supercurrent branch. So we have a finite supercurrent. Typically what you do is you current bias your tunnel junction, your circuit, and you can have finite current flow without any voltage drop. Around zero voltage, you have a finite supercurrent branch. And what you also have is, because you have this superconducting gap, the amplitude of this condensate actually gives me an energy gap which kind of protects this macroscopic quantum state to a standard kind of quasi-particle excitations, to thermal excitations and these things. And this gap you also see in the current voltage characteristics. So you have a supercurrent branch and a finite gap below which you don't have any current flow. Above the gap, you start to be normal again. Okay? This is essentially the Josephson effect. This was discovered by Brian Josephson. This is what we call the first Josephson effect, or the DC Josephson effect. This is the fact that we have current flow without any voltage as a function of the phase difference, as I mentioned. You have another effect, is that as soon as you have some finite voltage in the junction, you actually develop a time-dependent phase. Okay? and this gives you an AC current. So a finite DC voltage, instead of giving you dissipation in a superconductor, what would give you is an AC current, and this is called the AC Josephson effect. You know, and these are the early experiments where, again, you see this very nice, this is an oscilloscope, a direct image of an oscilloscope where you nicely see the current branch and this gap in the IV characteristics. For these discoveries, together with Ivar Giaver, who was the one doing the experiments, and also Leo Sacchi for tunneling phenomena in superconductor, they got another Nobel Prize. This is 1973. In particular, half of the Nobel Prize was given to Brian Josephson for his theoretical prediction of properties of supercurrent through a tunnel barrier. In particular, the phenomena generally known as Josephson effects. Third Nobel Prize related to superconductivity. So for the rest of the talk, I'll try to explain why this year we actually got another Nobel Prize for superconductivity. And what new discovery is being honored this year? What new discovery is being recognized as important enough to award yet another Nobel Prize related to this Josephson effect? The quote, essentially the quote of the Nobel Prize is the demonstration of quantum behavior of macroscopic electrical variables in a circuit. Okay? So we go from a kind of macroscopic phenomenon in the sense of, okay, we have electrons, they condense in a condensate, which is the Kuiper condensate, and then we do experiments with Josephson junctions, and we see some currents. Current and voltage, but current and voltage, what we measure in an oscilloscope is something classical, right? It's like a transistor, right? A transistor is related to quantum mechanics in the sense of, you know, we have semiconductors, we have a band gap, we have these kind of things we all know, and we have the transistor effect. But the current that we measure in a transistor is something completely classical. The same for the Josephson effect. But this Nobel Prize is for demonstrating that these currents and these voltages can be actually behave as quantum objects, as macroscopic quantum objects. And this is a step beyond, going beyond the classical circuit to a quantum circuit. All right, let's go to high school. Let's remember about the LC oscillator. You all know about the LC oscillator, of course. So an LC oscillator is the simplest circuit you can think of. Essentially, this is an inductor, and this is a capacitor. So half of the circuit has magnetic energy. Essentially, this is the flux, the magnetic flux, which is directly proportional to the current, and the constant is the inductance of such magnet. And the energy stored by this flux here is L times I square, or phi square over 2L. This is high school or first year physics, I don't remember, more or less. Material, very, very, very trivial. Capacitor stores electrical energy, the energy of a capacitor, C times V square, or Q square over 2C. And the voltage and the flux are related by this elementary relation. The time derivative of flux is given by a voltage. This is an LC circuit. All right, something that I'm sure you also know is that an LC circuit is just a harmonic oscillator, okay? You can translate an LC circuit and write the equations of an LC circuit like the equations of a harmonic oscillator. There is a one-to-one correspondence to a harmonic oscillator. If you define the flux to be your coordinate, phi squared over 2L is directly translated to x squared. This is your coordinate now, phi squared. And you know, the inverse inductance is the spring constant or your harmonic oscillator. The same for the momentum operator. The charge is C times phi naught here, which you can translate into a velocity, okay, or a momentum if you wish. And the mass of your particle is just the capacitance of the capacitor, okay? So capacitance is mass. 1 over the inverse inductance is the spring constant of your harmonic oscillator. Again, this is first year physics, or also in chemistry, you learn these things. Okay, so you have the harmonic oscillator, you have the LC circuit, and I told you about the Heisenberg principle. I told you that in quantum mechanics, there is this uncertainty principle which relates conjugate variables like position and momentum. So I made this analogy between the LC circuit and the harmonic oscillator, telling you that the flux is the coordinate and the charge is the momentum, meaning that if I allow myself to assume that this particle living in such potential with position and momentum being quantum, these two quantities, the same as the Heisenberg principle for position and momentum, will have a Heisenberg principle for flux and charge. And this is not my assumption. Actually, you can demonstrate formally that you can, what we call, is a bit more advanced thing, what we call to quantize the circuit. We can actually quantize the circuit. And Michel Devoret, actually one of the Nobel awardees, is one of the pioneers doing these things. You can actually put photons in such electromagnetic fields, quantize such photons, and end up with quantum expressions for flux and charge. But for this talk, the only important thing to remember is that position and momentum are fully equivalent to flux and charge in a circuit. So if they are quantum variables, they should follow quantum fluctuations. They should follow the Heisenberg's uncertainty principle. If they are a harmonic oscillator, they should follow the equation of a quantum harmonic oscillator. We all know from physics, when we learn physics, first thing we learn is the quantum world. The second thing we learn is the harmonic oscillator. In quantum physics, you all know, this is a parabolic potential which discrete levels described by this equation, where n is the number of excitations in the harmonic oscillator. So if I consider my harmonic oscillator being in terms of a flux, that I told you that is equivalent to the position, this is phi squared, this is a parabola. So all these levels would correspond to the discrete levels of a harmonic oscillator, that in my case are the discrete levels of the circuit. So this is like an atom. This circuit, when you quantize the circuit, this circuit contains discrete levels like an atom. Physically, this would correspond to the motion of plasma modes in the circuit, okay? You know, this LC circuit, as I told you, is an oscillator. Physically, is the oscillation of plasma modes in the circuits which gets quantized. So these photons are the plasma modes of this electrical circuit. All right, so I have my discrete levels, but still I cannot define a qubit out of them, because all these transitions in a quantum harmonic oscillators are degenerate. The energy separation between levels in a harmonic oscillators they all have the same energy distance. So if I want to manipulate my 0 and 1 in such a harmonic oscillator, I would immediately populate 1 to 2, 2 to 3, and so on and so forth. So with a harmonic oscillator, I cannot really isolate two levels, because all the levels are connected, okay? So I need something slightly different from a parabola. So I need to have some nonlinearity in the potential in such a way that the levels become slightly different in my potential energy, okay? So instead of having phi square of this harmonic oscillator, the dashed line, I need the blue line. I need some nonlinearity. And this is when the Josephson junction becomes relevant, because a Josephson junction is an inductor, essentially. No dissipation, remember? It's an inductor, but with a contribution which is a cosine of the phase. And this cosine of the phase is essentially what would give me a deviation from a parabola. Instead of phi square, I have a cosine of the phase, of the flux. Okay, I need to hurry up. I'm a bit slow. Okay, we had the harmonic oscillator with the LC circuit. When I put the Josephson junction, what I have is a pendulum. And again, the analogy is perfect. You have a pendulum. You write the equation of a pendulum in the gravitational potential. mgl, L is the length of the pendulum. 1 minus cosine of the phase. This is of the angle, in this case, of the angle of oscillations of a pendulum. This is a pendulum in a gravitational field. If you compare the equations of a pendulum with the equation of the Josephson junction with a capacitor, this is precisely the very same equation. So when you go from an LC circuit, harmonic oscillator, to the Josephson junction, you have the quantum pendulum. You have the equation of a pendulum in the circuit. All right, I need to hurry up. The Nobel Prize in Physics 2025 has been awarded to John Clarke, Michel Devoret, and John Martinis for the discovery of macroscopic quantum mechanical tunneling and energy quantization in an electrical circuit. John Clarke was the PI of the group, Michel Devoret was a postdoc, and John Martinis was doing his PhD in the group. This is the picture instead of the cartoon. The picture today, the picture more or less when they were doing these experiments, early 80s. And this is very kind of primitive device where they actually demonstrated these quantum effects in a circuit. So let me explain in 5 minutes how does it work. We have the Josephson junction. This cross is my inductor, which I have replaced by the Josephson junction. I have my capacitor here, and I have some resistor, some extra resistor in the circuit. So what I do is to flow a current through the circuit, and I can have 3 different contributions. I can have the current flow through the capacitor. This is Q dot. I can have current flow through the Josephson junction. This is sine phi. Or I can have current flow through the resistor, which is Ohm's law. When you put together everything, you have something which is not that relevant. This is what we call resistively and capacitively shunted Josephson model, which is this equation, this differential equation governing the dynamics of the phase. But what is relevant, again, coming back to the analogy with a particle with a mass and with a position, is that this particle lives in the cosine potential plus this contribution from the current bias that I put in the circuit. So this is a cosine potential which is tilted by the current. So you should think about this as a very fat particle which mass given by the capacitance of this capacitor living in this tilted Josephson potential. So something that you can tune with your current. So you go from this state where the particle, remember this is my position, which is the phase. My particle lives in this minimum of the potential, and then I tilt this with the current. I tilt this until the particle can jump into different minima of this cosine. When I jump, I develop a normal state. This is what is called the running current state, the normal state. And this is actually an image of the PhD thesis by John Martinis, 85, where if you Google it, you will find it, where he explains that what he wanted actually was to demonstrate that this particle lives in such potential, and that you can actually demonstrate that apart from thermal fluctuations above the barrier, you can actually demonstrate tunneling of this phase. So again, this is a macroscopic circuit. This is a macroscopic quantum variable, the phase and the charge, and they wanted to demonstrate the quantum tunneling of such huge object, which is the phase of this condensate. And indeed, they demonstrated tunneling of this circuit, again, using this idea that when you tunnel, actually I have a slide here, that when you tunnel through this minimum, you change the phase. The phase of your system is not fixed. It can fluctuate. It can have quantum fluctuations in the sense of quantum tunneling. And when you tunnel from one minimum to another, the time derivative of the phase is different from 0, meaning that you develop a voltage drop. So tunneling of the phase in this cosine potential translates in the circuit as a voltage drop. And you can actually demonstrate that this voltage drop actually at high temperatures, of course, is thermal escape, but eventually it saturates to a quantum limit. This is and there are mathematics behind these expressions. You can demonstrate that this phase actually undergoes quantum tunneling. And they also demonstrated, well, this tunneling, this is what I call in the quantum X, in the talk quantum X. You know, this is your phase with the ICMM mode instead of the egg. This is your cosine potential, you know, the barriers, the minima. So this is the experiment, right? You have the cosine, you tilt it, at some point, you know, if I tilt this, the ball stays there. But what they demonstrated is that this phase, this huge object, can have quantum tunneling. So this is the analogy with the egg, quantum egg. So you have something which is macroscopic. This is billions and billions of electrons at macroscopic quantum state fluctuating in a circuit. So charges and fluxes or voltages and currents, which are equivalent, are quantum objects in the circuit. So I'm done. Essentially, of course, this is a quantum well. So this phase lives in a quantum well with discrete levels. So this quantum phase lives in an atom, if you want. So there are discrete levels that you can actually perform a spectroscopy on these discrete levels, pretty much like you do in an atom, and you can actually demonstrate that you have very well-defined transitions in the circuit corresponding to these atomic levels in the circuit. So this was the first demonstration that this very primitive element with such massive circuit, which is actually a macroscopic circuit, behaves as an atom, essentially. Discrete levels, tunneling effect, and all these things. This is 85. Of course, you have to understand how quantum dissipation enters. This is the whole world of quantum dissipation, decoherence, Schrödinger cat, you know, all these things, how this phase develops a decoherence in the macroscopic world. And just 15 years after these early experiments, this was the first demonstration of a qubit out of such superconducting circuit, you know, Rabi oscillations, the things you learn in elementary quantum mechanics in a two-level system, Rabi oscillations in such a superconducting circuit demonstrating for the first time. This is, you know, 25 years ago, not that long ago, that the first qubit with a superconducting circuit was demonstrated. This was 15 years after the Nobel Prize. People were able, this is actually an experiment from Japan, Nakamura et al., where they demonstrated Rabi oscillations of macroscopic variables in a circuit, okay? This was the birth of superconducting circuits. From here to today, we have, you know, Google, IBM, all these huge quantum computers where people these days are demonstrating amazing progress. And with this, I think what is going on? Yes, with this I'm done. If you want to learn a bit more, this is an outreach article that I wrote for the conversation. Essentially, all these ideas about quantum phenomena in circuits and so on. It's in Spanish, but if you want to learn a bit more, you can go. And okay, thank you.
Thank you, Ramón, for this fantastic talk, showing us how quantum physics, from the beginning of the 20th century, was one of the guiding disciplines in physics, and now how we now transform to the second quantum revolution. We start with the second quantum revolution. Thank you. Then the questions for Ramón will be after the talk of Felipe. We are going to join the questions together, and then also we can discuss the connections between also the two Nobel Prizes and so on. Then we have opportunity to everybody from different disciplines to participate in the discussion. Then the next speaker is Felipe Gándara. I don't know if you know, but he was in Sweden this December, in the Nobel Prize, the private party, no, of I think was Omar Yagi, no. Then Felipe his research activity has been focused on metal organic frameworks. Between the 2009 and 2014, he worked as postdoctoral researcher in the laboratory of Omar Yagi. That is one of the awardees of the Nobel Prize of 2025. First in Los Angeles, and then later in Berkeley. No, all the two institutions joined, I think, to the University of California, if I'm right. Since joining to the ICMM, he has continued the advance of the research in these metal organic frameworks in collaboration with Yagi. His current research focuses on the design of metal organic frameworks, covalent organic frameworks, for applications related to energy and sustainability, combining synthesis and advanced structural analysis. His contributions to the field of reticular chemistry have been recognized with the Sagrario Martínez Carrera Award in 2023, that he was granted by the Grupo Especializado de Cristalografía y Crecimiento Cristalino of the Royal Society of la Sociedad Española de Chemistry, no? The chemistry, and also for the physics, no? Both together. And with the award of Alajos Kalman in 2025, last year, that was granted by the Hungarian Chemical Society and the European Crystallographic Association. Then now today, Felipe is going to talk us about the Nobel Prize and also his experience with awardee. Okay, thank you.
Thank you very much, Sarah, for the introduction. Can you hear me? I don't think it's working.
Está encendido, a lo mejor no funciona. Está colocado esto. Oye.
Okay.
Ahora sí.
All right. Thank you. Thank you.
Por los pelos.
That's right. Perfect. Thank you. So thanks for the introduction. As you can see, I cannot miss a chance to get embarrassed in front of my colleagues. And actually, that's going to be a little bit in the spirit of my presentation today, as you will see. And as Sarah was saying, I'm going to talk about the Chemistry Nobel Prize today. And this prize actually feels kind of personal to me because I had the opportunity to work as a postdoctoral researcher in the group of Yagi. It's not only that the field that I've been doing my research for basically my entire career has been recognized this year with a Nobel Prize, but also I had the opportunity to work with one of the laureates and seeing somebody that has been so influential in your life reaching this level of recognition. It feels really great. So it's been really nice. So I tried to make this, that's the second time I'm going to get embarrassed. So I don't know what's going on, sorry. Is this there? Okay, so where was I? Okay, I was saying that it's been, it's also, it's very related to my personal experience, so that's in the spirit of my presentation today. I'm trying to do it in a different way from what I usually do for my presentations, because I want to, in a way, show with this story how the development of the MOF field, which is basically the prize for this year, the development of metal organic framework, has been deeply linked to my personal vital experience, both professionally but also personally, if I could actually separate both aspects of my life. So with this being said, and I apologize then if the presentation is not what you were expecting, but I still hope that you can enjoy and learn a little bit about MOFs and how interesting these materials are, I think, and hopefully you will also have that feeling at the end of the presentation. So let's start with the prize, with the 2025 Nobel Prize. As I was saying, it's been granted for the development of metal organic frameworks. So I took this illustration from the Swedish Academy of Science that they use during the announcement of the prize, and I really like it. I think it's very illustrative, and they say that MOFs have created new rooms for chemistry. And I think I like very much this representation. I think it's true in a really broad sense that MOFs created new room for chemistry. You can see here how the molecules are really hanging out, having a good time, going inside cozy buildings there. But the nice thing here is that basically you can design and create buildings like in the real life we do for people. Now we can do that also for molecules where they can go together, the same type of molecules, but they can also be separated or just have a great number of molecules going inside. So I don't know if MOFs, MOFs are very popular nowadays, I believe. I don't know if anybody here doesn't know what is a MOF. I hope everybody knows. If nobody knows a MOF, raise your hand. So I'm assuming that everybody has an idea of what MOFs are, but nevertheless, again, from the press release, I selected some keywords that I think that are very important to know if you want to work and know a little bit about MOF and understand this material. So MOFs are made by the combination of two different building blocks, metal atoms and organic molecules. They are held together, typically by strong coordination bonds, so you can form periodic structures. So you have crystals, typically, because you have extended networks and they are periodic structures. So another thing important here is that they have the potential to be porous. So these crystals, they can contain large cavities and pores that can be accessible to this type of molecules. But also very importantly is that we can design the MOFs so that we can have them to behave and have different properties and capture, for example, different kind of molecules, or also have chemistry and reactions, chemical reactions going on inside the molecules. And those are very important features of these materials. But also when describing what is a MOF, I also like to take a step back and go into the very basic. So we know that atoms, they can form bonds among them and create molecules with a strong bond. They share electron density, and then we have coordination or covalent bonds. If we are doing with the metals, for example, and then we have molecules. But molecules are discrete entities, discrete units. They can interact among themselves, of course, and then you have an entire field like a supramolecular chemistry that was also recognized with a Nobel Prize back in the 80s. But there, the interaction between the molecules are not made by strong bonds, or they are typically weak interaction, hydrogen bonding, or halogen interaction, van der Waals interaction, and the kind. Although there might be some interactions and there is the possibility to have specific interactions between them, but these are not strong interactions. So we are still talking always about discrete molecules, discrete units that are together interacting. But why not going a step beyond there? And why cannot have the molecules creating bonds among themselves also, and getting the bonds extended in 2 or 3 dimensions so that we can create this type of frameworks and building. So something like that was probably thinking of one of our first laureate, Robson, back in the 70s, at least is what he said that during that time when he was a professor at the University of Melbourne. He's retired now, but he made his entire career in the University of Melbourne as a professor in Australia, although he's British. But he said that he was basically using this type of wood, ball, and stick models to represent the networks on how atoms, individual atoms, get these structures, particularly for inorganic solids, and during the classes. And then he thought that maybe that could be also translated to the field of molecular compounds and coordination compounds. So that was back in the 70s. So we have to jump a little bit to start our journey. So we have to go to the 80s, 1989. So by that time, the wall of Berlin was falling. I was 8-9 years old. Most of my scientific knowledge could be actually found in this textbook that many of you probably know. And actually, my parents were more worried about other aspects of my education by that time. I became a little bit of disappointment to my mother in that sense. But anyways, so in the 1989, at that time, this paper came out, and this is one of the most important ones in the, at least for how Robson got this prize. So he chose this type of network, which is the same that diamond has. So in diamond, you have carbon atoms that will be here where we have the balls, and they are directly connected, the carbon atoms, to form the diamond structure. So he deliberately designed or chose a molecule that could have the same type of network, the same topology. All right, so he got this tetracyano type of molecule, which has the same tetrahedral shape, and copper atoms that are also known to have tetrahedral coordination environment when you have them connected to the cyano-ligands. And he crystallized this structure that is topologically equivalent to diamond. So that was the first demonstration of a network that was deliberately designed to have a specific topology and described based on the standard structure. So coordination compounds with a standard structure were actually known before this work, and there were some descriptions back in the 50s actually of standard structure. But the key point here is that he designed and he chose a specific building blocks to get one particular network and not any other. So he continued with this work and made other networks extended to different topologies. In topology, we care about the connectivity. We don't care about what are the chemical components, but just how they are connected among themselves, the different nodes in one network. Okay, so other examples, for example, here showing how instead of tetrahedral, you can also connect square-shaped ligands. And if you have this type of square-shaped ligand with, again, tetrahedral, you will have the same network that you have in other inorganic compounds like copper, like platinum sulfide. In platinum sulfide, you have, it is called PDS, you have sulfur and platinum atoms with the same square and tetrahedral coordination environment. So that was published already in the 90s. And here, notice that in this paper in Nature he was mentioning, they were mentioning there were a network with large channels. But here we are talking only about channels, not porosity yet. I will go that in a minute. So just to mention that this work by Robson actually connects really well with the classic works, for example, by Wells, in describing inorganic solids based on the connectivity of their components. So that language, that topological language, that rigorous language was already applied for inorganic solids, and he translated that into the field of coordination compounds. And that was a first start for the MOF field. And there are also a couple of important implications in Robson's work. So first of all is that he demonstrated that that it is possible to crystallize compounds with a standard network, coordination compounds with a standard networks. And why is this important? Because when you are crystallizing something, typically you need some degree of reversibility. And then to have that, the stronger is the bond between the components that make up your crystal, the more difficult it becomes to get something crystallized, because you need some reversibility to correct the defects that happen when there is some crystallization. All right, so in coordination, it was typically accepted that if you have multiple bonds, at the same time you will have just some amorphous junk rather than having some crystalline material going on from your reaction. And on the other hand, you are doing the crystallization at the same time that you do the reaction, the chemical reaction between the different components. So you have to choose the right conditions for this to happen. Another important implication is about porosity. So it was already noticed that this type of materials, they have a lot of empty space inside. When you have these networks, inevitably you will have empty space that is not occupied by the molecules that are building the framework. Now, in the case of Robson's compound, they were filled with counteranions. The ligands that he used, they were neutral. So when you are using metal atoms, then you will have counteranions in the pores, and they cannot be removed. And also there are solvent molecules inside. The strength of the bonds in these coordination compounds was okay, but it's not too high. It's not, it was not possible yet to remove the solvent molecules and to get accessibility to the pores. So tackle this problem and to solve this, we have to jump a little bit more, go now to the 90s, another exciting time with a lot of great music and some interesting movies going on. And also during this time, our two other laureates, Kitagawa and Yagi, they started to publish some works addressing these two important issues regarding the robustness of the frameworks and accessibility to the ports. And I will go and describe some of this work in a minute. So Kitagawa was, he made most of his career, basically entire career in Kyoto. He was sometime in Tokyo, but for not so long. And he's still a professor there. He's retired, but he still has a special position so he can continue with his activity. Yagi, on the other hand, he at that time in the 90s was a professor at the Arizona State University. He's the youngest among the three, but he moved from Arizona then to Michigan, UCLA, and Berkeley. So he's been jumping from one institution to another until now that he's actually a university professor. It's not just University of California, Berkeley, but he's University Professor of California System, which is actually a big deal in the University of California system. Is a great recognition also there. So this work in 1995, when Omar was in Arizona, it was published in Nature, where he was showing that actually it is possible to have molecules diffusing inside the pores of a metal-organic framework. By that time, the term metal-organic framework actually was adapted. It was coined in this paper and another one before. Before that, coordination network, coordination polymers, all the different terminology were also used, and still some people is using one on another, although we are going to stick to MOV into this for this talk, of course. And the way he did that was by using charge linker. So, but at this time, there were many groups also already synthesizing coordination networks, extended structure, and so on. But then he decided to use this type of linker, in particular carboxylic derivatives, so that on one hand, the strength of the bond with the metal will be higher. It will be produce more robust structure, and on the other hand, you will have now the possibility to have neutral networks. And then you don't have the counter anions inside. You can have other species replacing these molecules that are in the pores. Another important paper, and I apologize for the figure, for the resolution. We have to do some changes in the computer, but that also gives you an idea that this is for almost 30 years old paper. It was the first demonstration, in this case by the group of Kitagawa, that the material can actually have gases, molecules, diffusing inside in a reversible way, and with the structure being intact. So he performed this experiment, although it was made in the high pressure regime, up to 30 atmosphere, where molecules of gases like nitrogen or oxygen were diffusing inside in a reversible way in this type of MOF structure, and the structure will not collapse. So it will be reversible, and you could have the gases going in and out. So it was the first demonstration, very important, that gases can go inside the pores, and the pores are accessible there. Now, already in the early years, Kitagawa was actually doing a classification of MOFs and coordination polymers based on their stability and on their behavior when you have the gases or molecules inside. So the first generation will correspond to these molecules that are not, or these compounds that are not able to maintain their structure after desorption, like the Robson's compound. Now the second generation will be stable frameworks. You can have the gases inside and outside going in a reversible way, maintaining their structure. And at that time, he already envisioned a third generation of materials that have a dynamic character. Okay, so they have materials with a structure that can adapt, and they may have changes in their structure, for example, expanding or contracting their volume when you have gases going in and out. So that was envisioned, and it actually became very popular, this type of materials. For example, the breathing MOFs are known, that were developed by a group in France by Ferret, and later by other groups in Europe and other places in the world, where you have materials that, when you have the gases, they can expand and increase their volume, but then they return to other states. So So this perspective by Kitagawa was actually very relevant because he considered not just the MOF architecture, it also underlines the dynamic behavior and highlight how important it is to consider not just the topology of the material in the ideal state, but also the different pathways in which the structures can be deformed, can be rearranged in response to many different stimuli, like gases, like pressure, anything. So most of Kitagawa's compounds during the year and most of his work, he's been describing the absorption and desorption process, for example, not just as a passive process, but something that triggers also a response in the material, and that was very paradigmatic, I think, because the idea that a crystalline solid behaves as an adaptive system rather than something that is not doing anything, it's as I'm saying, it's very paradigmatic. It changed also a way in we were seeing these compounds. And many of his work, as I was saying, he focused on these materials not just in the preparation and in their use, but also characterization with advanced technique and seeing how the different possibilities we have for the material. So I'm going to jump now to mostly to work by Yagi, going back again to the 90s and see how also the field evolved during this time for porosity. It was in the late 90s. At that time, I already went to university. I enrolled in the chemistry degree at the University Autonomous of Madrid, but I was still unaware of anything about ICMM, CSIC, that even know that this building was here in campus. I just stay over there, close to from the train station to the science building, and also worry about other important things, like football or communicating with people in the computer. You could spend hours. I don't know if you guys remember this thing, but you could spend hours in the computer just chatting there. So, anyways, in 1998, so this paper came out with a group of Yagi. He continued with the same carboxylic linkers, and now MOF2 was the first material that was reported to have microporous behavior. Now, this is another demonstration of porosity, but this is also very relevant because it is made in the low pressure regime. So this is a sorption isotherm. This is the first sorption isotherm reported for a MOF. And typically here what you do, and this is something that this is a gold standard to characterize porous materials. So this is what you do with any porous materials. You take it to very low pressure, high vacuum, and then you start dosing small amounts of gases, like nitrogen at 77 Kelvin, like behaving like a liquid, and then you see how the different the different amount of gases are taken up by your porous materials. With that, based on the shape of the isotherm and based on the amount, then you can describe your materials being microporous, mesoporous, macroporous, and also importantly, you can also quantify the surface area. Okay, so you can compare different materials and their porosity, and the first MOF surface area was reported to be around 300 square meter per grams. That was a modest value, but was comparable to other, for example, zeolites and other inorganic solids. But as I'm saying, that's very relevant because it was the first time it was made for a MOF. So the MOFs, now they are not just some fancy structure, beautiful crystal structure, but they were also useful. They could also have gases coming in and out, and not only gases, but many other species. But to me, the real game changer was MOF5, and I think for many people, probably you have seen this type of representation of MOF5. I think it was also brilliant that they put this yellow ball. I don't know if you have seen before, but the yellow ball, basically that it wants to highlight the empty space. Because important here is not just the framework, but is how much empty space there is in this structure. And that was represented by this yellow ball. So MOF5, published in 1999, it had these building blocks based on zinc carboxylate clusters and this benzene carboxylic linker. So very simple building blocks, but when you have them together, you have a structure that is very, very porous, actually. And in this one, following this approach based on the carboxylate linkers, the material could be fully evacuated. The first surface area reported for this compound for MOF5 was 2,500 square meter per grams. So that was unprecedented for any other porous material, crystalline porous materials. Nobody has seen this type of values of porosity in a coordination compound. And that attracted a lot of attention from the scientific community, from the academia, but also from companies, for example, BASF, who made a huge investment in the development of the MOF field, actually. And that's something that has to really be recognized, too, because they also saw a lot of potential there, and they made a large investment in having, on one hand, the MOF developed on the basic of the chemistry of the field, but also trying to have these materials commercialized and take them to the market. So MOF5 is important, it's iconic because not only because of the high surface area, but also it helps us to show what are the design principles that comes with what is now today known as the reticular chemistry field. Okay, so if we look at the MOF5 structure and the building blocks that I was showing in the previous slides, you see that we have this type of clusters that have 6 points of connection, 6 points of extension that are disposed in an octahedral shape. The linker is linear, but as we know already, also from Robson's work, it doesn't matter how long is the linker, as long as you keep the same degree of connectivity. All right, so if you have the MOF5 components, you will basically always have a primitive cubic PCU type of network, regardless of what you have a linker with 1, 2, 3, 4 Benson rings, as long as the connectivity is always the same. So this is the theory, but we have to go a little bit jump again. 2002, that's also an important year, not only for the MOF community, but we'll see also it was also important for the MOF here at ICMM. And in 2002, this paper came out. That was a very important paper where this principle of isoreticularity was indeed demonstrated with this family of compounds. All right, so here you can see, and in this paper they reported this, how you can have all these series of compounds with the same secondary building unit, the same carboxylic, the same tetrahedral zinc cluster, zinc oxo cluster, and combined with a series of linkers with different lengths, different chemical functionalities, all of them giving the same topology, but with different pore sizes, surface area, but also decorating the interior of the pores with different chemical functionalities, for example. And this is important because it really shows that isoreticularity can be used as a design principle. It's not just we have a family of material that can be expanded and can be modified. And this has been used over the years, not just with this, but with many other type of secondary building units. You can basically use almost any element now in the periodic table to create MOFs with different type of secondary building units, inorganic secondary building units. Also, for example, you can change your organic linker, have different connectivity numbers, then you will have different type of networks. We are not having the same simple diamond PCU network. We can have something more with high complexity because we have different type of connectivity here, and it has been used. For example, I remember back in the early days there was this race to see who was able to publish the material with the highest surface area values. Back in 2012, some materials were reported to have more than 7,000 square meters per gram. Imagine this is the surface area of a football field, and you have it in 1 gram of some of these materials. So that was pretty impressive. And that was made thanks to these principles of design, so to this design principle of isoreticularity and the use of carboxylic linkers and the secondary building units. So 2002 was also an important year for MOFs, but now here at ICMM, these 2 papers came out here from our institution. The group led at that time by Ángeles Monge and Enrique Gutiérrez Puebla. They published these 2 papers using other organic linkers and different metal atoms. They actually came from a field working with oxides many times. They had also a strong crystallographic background. So it actually came, I think, very naturally to them to jump to the field of metal organic frameworks and to the description of compounds based on their topology and on their structure. So this group became later my PhD home. At 2012, I was still in the latest year of my career. A couple of years later, actually, I started to work with Miguel a little bit before I started my PhD with Nines. But in 2005, I started that work, that PhD, and I had the chance. It was a very exciting time to be trained in MOF chemistry because there were a lot of applications and papers going on for metal organic frameworks. So I was very lucky to be trained in synthesis of the materials, a lot of crystallography and structural analysis, but also on topological analysis. I actually made a short internship in the laboratory of Davide Prosepio in Milano, in Italy, during that time to learn more about topology. And Davide was actually a friend of Yagi. They knew each other from different events in the past since they were very young. And Davide was organizing this school in the University of California, Santa Barbara in 2008, while it was just in the middle of my PhD studies. So he told me to go there. I attended, and he suggested me to apply for a postdoctoral position with Omar. Omar was one of the lecturers, so I talked to him. I told him that I wanted to apply to his lab. He thought that I was actually trying to be a PhD student. I was looking really young at that time, so he didn't even think that I was applying for a postdoctoral position. Anyways, I came back to Madrid, sent him an email, and as I was expecting, got no response. And just a few months later, actually, Davide told me, he sent me an email asking whether I had any news from that application. I told him that I didn't have a response from Yagi. Yagi at that time was already kind of famous already. He was publishing a number of papers, very important papers in the MOF, and he was very well known in the community. And when he learned that I didn't have any response, he sent him an email. Basically, like 15 minutes later, something like that, I got an offer from Omar to go to his lab. So I got my thesis defended in 2009. Here in this very same stage, and then moved to UCLA. I gladly accepted the offer, and then go to America. And so during that time, a lot of changes were happening. Everybody was very happy in 2010. You can remember I became a postdoc, but not only a postdoc. Other aspects of my life were also changing, and the MOF field was also evolving in many exciting ways. For example, this is also a very important paper, I believe. It was published then in Science in 2010, and that was where the concept of multivariate MOFs was also first described. I remember going in one of the first group meetings, and everybody was talking about MTV MOF. And I was like, what is MTV MOF? I was actually kind of afraid of asking because, just arrived. And then I told Omar, what are you talking about? What is this NTB concept? It was not published yet. And then he explained how you can have MOF crystals where instead of having one linker, you can combine linkers with different functionalities that are appended to the backbone of the molecule. So the connectivity remains the same. You have these linear linkers, but then you append different functionalities, and then you mix them together. And instead of having separate phases, different crystals, you have one crystal with a heterogeneous environment inside. So that was another strategy for designing MOF that changes a lot the field and is used today in many applications to change the properties of the materials. By that time, the bonds between ICMM and the group of Yagi were also getting stronger. In 2011, actually, Enrique, he was the chair of the organizing committee of the IUCR, the International Union of Crystallography meeting. This is an important meeting. It happens every 3 years. In 2011, it took place in Madrid, and they had 4 plenary lectures. 3 of them were the 2009 chemistry Nobel laureates, and the 4th, according to that you can see in the IUCR Congress report, Omar Yagi gave the 4th lecture on metal organic frameworks. So it actually had 4 Nobel laureates that conference. And not only that, Omar and Enrique and Nines, they became friends, and Omar invited them to go and visit the labs and be there as visiting professor several times during the past almost 10 years. So as a postdoc, I had the chance to participate in different projects, expanding family, expanding pore sizes, like in this paper that was reported also in 2012, where again, following this design principle, we could have pore apertures larger than has been reported before for MOFs, avoiding, for example, interpenetration and other problems that you have when you keep expanding the linkers. That was a paper actually also in collaboration with a group of Stoddard, who was at Northwestern. Stoddard also became a Nobel laureate later on. And here we show how we can actually have large molecules like proteins diffusing inside. Also, one paper that I also very fond of is in this one that is related to water harvesting application. So this is a very exciting project. At that time, people were investigating MOFs for water sourcing processes. You can have the MOF absorbing water molecules, and then you can use, for example, at that time the interest was in using them as thermal batteries. So basically you use the energy that is released during this process of sorption and desorption to have what is called thermal batteries. Now Omar here envisioned a different application. I remember that when we were discussing about writing this paper, he said that we could use actually this as a water harvester. What this means is that you can have a MOF that is absorbing water from air during night, and then during the day it will release these water molecules, and then you could have this used for example, to deliver water in areas where there is no supply. Later on, also you can see, for example, well, there are many applications and many groups working on this. This is one of the most important applications. This paper has been cited over 2,500 times. So there are many people working on this, and this was one of these of the first time that it was proposed for this application. If you have the opportunity to see the speech that Omar gave during the Nobel banquet, it's online in the Nobel Prize, you will see that he's actually talking about this application and how it's also linked to his personal experience. Omar is actually a son of Palestinian refugees who were to Jordan. He was born in Amman, and when he was a child, actually he was living with his family, many children, livestock, all in the same building, in the same one or two rooms house, and with no water supply many times, and they had to wait for the government actually to bring water with trucks. So the application of having water delivered to places where you don't have these supplies or where you don't have fresh water was actually something that also comes from personal experience. So I'm coming to the end. I'm very close to finish. And at this point, probably you have noticed that up to now, I didn't really talk much about the application of MOFs. But that was actually on purpose. When I started working on this field almost 20 years ago, the question that we constantly had was like, what are MOFs good for? And of course, we could always answer this with this application: carbon dioxide capture, catalysis, drug delivery, now water harvesting. And now MOFs actually are commercially available. There are many companies now that are marketizing MOFs. For example, this is in Canada, MOFs that are able to capture carbon dioxide directly from the air. There are also these devices for water. Sorry, there are also even applications for protection in the military against warfare agents and toxic gases molecule. But to me, this Nobel Prize is not just about the application. I don't think this is the central point. So I think that the prize, what really recognizes are these design rules and the conceptual framework that Robson, Kitagawa, and Yagi, they have provided the community. So now the idea that you can have and that you can treat metal clusters and nodes, organic linkers and nodes of a network, that you can have a material that can be isoreticularly expand and design, or that you can have MOFs that have this flexibility and dynamic behavior. That's something that has provided the community with a toolbox to design porous materials, really. And I think that this is more important than a single application or a device. And because once you have this toolbox, then applications will follow. So, and MOFs nowadays are present one way or another, I think, in research programs all around the world. And now the key contribution, I think, is this chain of the question. It's no longer, what are MOFs good for? It's when we have a specific scientific problem, which MOF can we use, can we design to tackle and to address that problem? And I think that's really what is in the spotlight of this Nobel Prize. And these are pictures I took in the Nobel Prize Museum back in Stockholm. I don't know if you've been there, but in the museum, basically, the laureates, they give some personal items to be there in the museum. And when you see this now there, along with this giant of science, you see how MOFs now are part of science. And I think that was pretty nice to see. So it takes me to the end of the journey. So the prize was very much celebrated, and I was very happy to show you today, and happy to have any question now. So thank you very much.
Thank you, Felipe, for the talk, also for these personal thoughts. Yeah. Then I think that we are going to start with the questions. We are going to do like a round table. Okay, then I would like to do a connection between the two Nobel Prizes, because usually physicists, especially in quantum physics, we love everything very ordered. That is what, in principle, is doing in MOFs, no? You're getting these reticular structures. And in quantum physics, we usually try, in this kind of devices that you define today, like the superconductor quantum computer, we need to cool down the systems, no? Then we need to cool down the temperatures to very low temperatures, and then the integration of this kind of quantum computers in the real world makes that extremely difficult, no? It's very difficult to make one of these quantum computers. Then do you think that we can be inspired by complexity in molecular systems to do a different approach to this quantum phenomena in order to develop new alternatives that could be working in room temperature, because usually molecular systems, they work in room temperature, and probably we take advantage of reticular materials. What do you think about that?
So yes, yeah, I've been discussing today in relation to the Nobel Prize these superconducting circuits, but there are other approaches, and they are I mean, it's not related to MOFs, but related to atomic physics. So there is a very powerful approach called Rydberg atom, where precisely what you have is very well ordered arrays of hundreds of very excited, Rydberg atoms are atoms which have very highly excited states, and using these arrays of rubidium, cesium, I believe, atoms, they are able to construct huge arrays of perfect order atoms. In Harvard, they are pioneering this Michel group, and there is actually a company with a quantum computer using Rydberg atoms. So the answer is yes, you can use other approaches closer to chemistry or to perhaps atomic physics. There's also the molecular spin. There are other proposals for using molecular spin arrays. This is not that well developed, but there are some prototypes using molecular spins. So yeah, there are many ideas.
Yeah, because in principle in colatoms, no?
Yes.
Colatoms, you need also to cool down. It's true that you can use light, no?
Yes. So.
But you need also to cool down the system.
Right. So yeah, I don't think this is actually that of a problem, in the sense that I mean, a quantum computer is not something that you're going to have at home. So it's like artificial intelligence these days, right? You have some data center where you run your open AI, right? So a quantum computer is the same. You will have a lab in, actually IBM, you can run codes these days in IBM. They have a lab in New York State, upstate New York, and you connect online and you run your codes, the same model that they are going to use in San Sebastian. So, a quantum computer is nothing like something we will have everybody. It will be like a huge infrastructure where you can run your codes. And this is, in that sense, low temperature is not that relevant. So you have your lab, you cool down, and you can do your computation. But there are platforms where you don't need such low temperatures. There is, there are other options.
Okay. Thank you. Then any other questions? Yeah, please.
So in this line, when do you think that a research center or whatever center could access to a quantum computer and to run the codes. To run the codes. When do you think the state of the art and when will happen that, for example, in ICM, we will use a quantum computer?
You can use a quantum computer now if you want. So thank you for the question. So yes, so you can use a quantum computer right now. So there is the IBM quantum computer where they already have this IBM quantum computer in New York. They moved to outside the US, and in San Sebastian they already have the quantum computer. The IBM, I don't remember the name of the generation, one of the next generations. They're already building the quantum computer there. But the level is still they are at the benchmarking level, in the sense that what you can do is to run algorithms at the level of research projects. So it's not like, you can do quantum computation at the level of what they call quantum advantage, like being able to do computations you cannot do in a supercomputer, like Mare Nostrum or whatever. This is not possible these days, but going online, and IBM Quantum Experience is actually a web where you can, there is a free model, 5-qubit model, which is free. You just connect this afternoon, you open an account, and you run a code if you want. It's very easy, actually. And then they have other models, like 100-qubit models, or a bit more advanced models for companies or for research institutions, where you pay more and you can actually, write your algorithms and run them in the computer. This exists already. Or banks, banks already use these computers to benchmark their finance algorithms or whatever.
You want no more? Then let's go to the to her. Yeah, I think that's what
Thank you. I have a question for the MOFs. Can we find any MOF in nature, or do they have to be synthetically made in the lab?
They are mostly synthetic. I think there was one that it was reported that there's some minerals made of oxalic acid, and I cannot remember the metal element that actually appears in nature. I cannot remember the exact name of the mineral. But other than that exception, they are mostly synthetic.
Thanks.
Yeah.
Thank you very much for both talks. This is my question for Ramón. I remember attending a John Martinis seminar back in the Niels Bohr when I was working there, and thinking, wow, this is amazing, because they were doing error corrections, they were doing really real energy levels calculations, and I was working in quantum photonics. And I thought, we are wasting our time here. I mean, these guys are. Do you have the opinion that there is a gain in technology in these quantum technologies families, and they are really?
Not really.
No.
Yeah, thank you for the question. Yeah, so we are at the level that there are a few existing technologies. The Rydberg atom is very advanced in the sense of very clean and very ordered arrays of quantum of qubits, but then the manipulation is lower. Then you have the superconducting qubit, but integrating this into we are talking about hundreds these days, but if you really want to have this, what they call the quantum advantage of really being much more powerful than a classical supercomputer, you need hundreds of thousands of qubits. So, from the engineering point of view, having such a massive array of superconducting qubits, which are pretty large objects, they are micron size. You need thousands and thousands of micron objects inside a circuit with cables, from the point of view of engineering, these days, there are photonic qubits, like, for bosonic sampling, for sure, there are different ideas. Nobody knows, I would say. So there are like other prototypes, like if they exist or if they are able to demonstrate these prototypes, They were much more powerful than superconducting qubits. There is also semiconducting qubits, using spins in a semiconductor. This is a bit less advanced than superconducting qubits, but if you are able to fabricate in a controlled manner semiconducting qubits, then this is huge, because then you have in a MOSFET, in a real MOSFET foundry, you can fabricate like semiconductor industry with transistors, where they know how to fabricate billions and billions of transistors at the same time. So semiconductors, there's a lot of progress and there's a lot of promise for semiconductors. But the answer is no, nobody knows really. Thank you.
Thank you. More questions in the audience?
Thank you for both talks. I have a question for each. For Ramon, for instance, I think you have little faith in your own topic, because it took 50 or 60 years from the quantum revolution, from the definition of quantum mechanics to the personal computer, 25 to 85. So what is your prognosis for the quantum personal computer? It might happen. Your reasons for not making them is very it's very strong, because now we are even letting our technologies reside elsewhere. We don't need very powerful computers, because we call these data centers and they bring us the answers. But if there were room for a personal quantum computer, we only have to wait a few decades and it might come.
I mean, these days it's not possible. I mean, I see the idea of having this. As I said, the first superconducting qubit was in '98. I was a postdoc in Delft, and Nasu Nakamura was actually visiting Delft, and I remember him giving the first talk about this in '98. So it's a few years back. And they are already doing this, quantum correction, Google, IBM. So it's in a very short time, they've been able to do this amazing progress. But this is at the level of very big labs. So I can see something like in 10 years, maybe less, to have a super powerful quantum computer in Google or Amazon or IBM, something like this. Personal computer, to be honest, I don't see this happening in at least 20, 30 years. But maybe I'm wrong, I don't know.
I see the progress in MOFs very tied to chemistry, but because I have some relationship with MOFs, which is more photonic, I wonder if you can do two-dimensional stuff and like epitaxial growth of solids led to the transistor and the first quantum development of devices which are actually useful and we carry in our phones. Is there a line of research or a potential development in doing two-dimensional stuff and with that layer structures with applications depending on this kind of layers?
Well, I cannot reply for the physics part, but for sure there are two-dimensional materials already created for MOFs, but also for other materials that they don't have in metal, like covalent organic frameworks that basically follow the design principle of MOF, but just with organic molecules. And there are many of them that have been reported to grow as two-dimensional materials. And you can grow them on substrates, and you can also exfoliate later on. And it's basically if you follow these design principles, you can choose what is the type of two-dimensional network that you want to have, select the right building blocks, and then you could have them. Now,
mostly focused on vector structures. Doing a MOF lead to a different MOF, something
Oh, yeah, that also has been made, I think. Yeah, like growing one on top of the other and sandwiches. Yeah,
And
definitely.
then you can attach molecules with specific functionality.
Right. So there are a class of how they call them surface MOF. So you can have the surface functionalized, or now you can do it even with unfunctionalized surfaces, and then you can have the MOFs growing layer by layer. Definitely, yeah. So then how you tie that to the specific application, like the one that you guys are discussing, I don't know how you do that, but if you have in mind what kind of molecule, what properties you need to have in your layer, you have these tools to create the material now.
Okay. We have another last question, please.
Thank you very much, both, for both talks. Were amazing. I have actually like two questions for Felipe. The first one is this Nobel Award has been recognized as basically the discovery of the MOFs. So do you expect that in future we should expect like new or more Nobel Awards related to the MOF field?
Well, yeah, I mean, the award says development of metal organic frameworks. But actually it goes just to metal organic frameworks. So one thing that they were actually being talked is that all the materials that, also as I was mentioning, also related to Cefe's question, like GOFs or other types of materials that can come also from this broad reticular chemistry field, they may also in the future, who knows, be important. And now, again, also relating to what I was saying at the end of the talk, is that now this is, for the past years, this is now open to all. MOFs are present in so many research programs. So if you want to, for any application, you basically can do it also. You can also use MOFs. So who knows? They could be present in the next breakthrough application. Why not? But for sure, the field has grown so much, and there are so many research groups that they can have all these tools now. For them, so yeah.
Yeah, thank you. And also the second question was kind of related to this. What do you think are the most important trends in the MOF field for the future or for the near future?
Well, that's a really good question. I wish I had the right answer to go and take it to the lab, but I don't have the answer. But I have the opinion that is also probably biased by our own research. And I think one of the things is related to how we can now increase the complexity of this material. So we started with simple MOFs where we have one component or two components growing and getting this structure, but we can think now of having different components, different chemical components, and then you can have the heterogeneity in the materials, and then you can have in one simple materials one part that is compartmentalized with one property and another with a different one. And then we can encode and change the properties also at the atomic level. And that could also probably can be also related to a new physical phenomena. For example, if we can control how the different chemical components are disposed in the materials, then we can also hope to have new properties emerging from these dispositions. So yeah, for example, I think that there is a lot of exciting things that hopefully will happen soon in the MOF field. So, then I would like to thank you again, Ramón and Felipe, for this nice talk. And, before we leave, the people who want to have the attendance